Okay, so hi everyone. In this class, we will study. In the last class, we have studied what is called. We have studied the properties of derived subgroups, uh, and this class we will define what is the lower central series, and we will see how it characterizes uh, nilpotent groups. Okay, so lower central series. So, yeah. So let G be a group. Define uh, chain of, so in this case it will be decreasing. Define a chain of decreasing subgroups, which usually we call it as GI, in the following way. Okay, so we define G naught to be G, and we define G1 to be the derived subgroup G comma G. And what we define G2 to be? G2 we define as G comma G1. Okay, and this will be obviously be a subgroup of G1, which is G comma G. The reason is G1 is a subgroup of G. Okay, and uh, we define like this recursively as Gi plus 1 is the commutator, the commutator subgroup, the commutator subgroup of G and Gi. Okay, so the chain, the chain G naught, G1, G2, and so on is called the lower central series. Okay, it's called the lower central series. Um, so this is the lower central series. Okay, and let me just point out here that all the uh, all properties similar to upper central series also holds for lower central series. And to be very precise, what are the properties I'm talking about? Let me just list out one or two of them. First one is, if G is a finite group, this chain has to stabilize at some point, because the if it doesn't stabilize means if orders are keep on falling, are becoming lower and lower, which can't happen if it's a finite group. So if if G is finite, this chain has to stabilize at some point. Second is, if there are two terms in the group consecutively which are equal, then from there on all the terms are same. That is, the chain again stabilizes at that point. Okay, and I think that is the two main important properties which also holds for lower central series. Okay, now I said that this lower central series somehow characterizes the characterizes nilpotent group. So let me make it clear what I meant by this. Okay, so theorem, let G be a group G is nilpotent of nilpotency class C if GC is 1. Okay, and C is the uh, let me put it in this way. G is nilpotent if and only if GC is 1 and C is the smallest such integer. So yeah, C is the smallest such integer, and also in both the cases the following equality, the following inequality holds. So what is the inequality? G of C minus I is a sub of Z uh, Ig, okay, for I equals 0, 1 to C, okay, and also uh, this is same as writing G of I is a sub of Z of C minus I of G for all I from 0, 1 to C. So both are same. Okay. So let's try to prove it. So proof. So we prove this direction first. Okay. So let G be nilpotent. Let nilpotency class C, that is ZC of G is G and C is the smallest such integer. Okay, so we first show by induction Gi is a sub of Zci minus 1g for I equals 0, 1, 2, 6. So that is what is my aim. First we show this inequality. See, my aim is to now show what? My aim is to show that GC is 1, right? But we will show this first, and from this it will just follow that GC is 1. So let's write down. So proof of uh, proof of. So just let me see what I wrote. So yeah, proof of GI is a sub of ZCI C minus IG. Okay, by induction. Okay, so let's see the case for I equal to 0. Okay, so for I equal to 0, For I equal to 0, what is G0 by definition? See the first slide, what we wrote. What is G0?
G.
G. So G0 is G. So, okay. And what is ZC minus 0 of G? This is just ZC G, and which is what we just saw here, right? That is also G, right? So this is also G. So what do we know that hence uh, G naught is a sub of Z naught ZC minus naught of G. So for I equal to 0, it is over. Okay. Let's now assume uh, that the statement is true for I equals K. That is uh, G, uh, that is GK is a sub of ZC minus K G. Okay. So we want to prove for I equals K plus 1. So what do you want to prove? That is GK plus 1 is a sub of ZC. Here be careful, it K plus 1 is in bracket. Okay, it's ZC minus of K plus 1. Okay, so we want to show this. Now, uh, see, let's see what is now. What is GK plus 1? GK plus 1 is nothing but G, G and GK's commutator subgroup, right? But then we know that this is true. So what will we get is from this we will get that this is a subgroup of G ZC minus K G. Okay. Hence, hence it is enough to show this commutator subgroup of these two is inside ZC minus of K plus 1 G. Okay. So that is what we want to prove. So our now main idea is to prove this. If we prove this, it is enough. So let's go to the next slide. So let's write down again what do we want to prove. So therefore, want to show the commutator subgroup of G and ZC minus K G is a sub of ZC minus K plus 1 G. Okay. Okay. So you know how to show something is a subgroup, right? You take elements of the smaller set and show it's in the bigger set. Okay. So what we do is now here element in this a general element is not just a commutator. It's a product of commutator and its inverse. But then it is enough to show that one of the commutator is one of the generator which are the commutators are there, and then from that it can follow that all other elements are will be inside it. Okay, so let's do that. So let x inverse y inverse xy be a generator of g c minus k g, that is x is a element of g and y is a element of z c minus k g. Okay, so I want to show that that x inverse y inverse xy is in z c minus k g. Okay, see, but what do we know about z c minus k g? What is the meaning of this? How is it defined? How is this? How was this series defined? Z of something. So to find what is this, we have to take g quotient the previous term in this series. What is the previous term in the series? That is z of c minus k plus 1 g. Then we have to take center of this, right? And then this will be a subgroup of the form something quotient z of c minus 1 k plus 1 g. That is how it is defined. Okay. Now you see something nice is happening. So now you see this y is in z of c minus k g, right? So what does it mean? That means so this will imply that y z c minus k g is in the center of g of z c minus k plus 1 g. So what is the meaning of it is in the center? It commutes with all such elements of this, right? So what will it mean that y z of c minus kg into x, no, sorry, there is something I have written it wrong here. This is not coset is from uh, c minus k plus 1. So what will it imply is, let me write down. So what will, let me write down here. So what will it imply is y z of c minus k plus 1 g in in product x z of c minus k plus 1 g is same as x z of c minus k plus 1 g into y z of c minus k plus 1 g. That is the meaning of that this element is in the center, right? That it commutes with all other elements. Now we just need to rewrite it. So what is the first? What is the left hand side of the equation? It is yx z of c minus k plus 1 g, and this is equal to xy z of c minus k plus 1 g. Okay. Now when are two cosets equal, you know that g1h is equal to g2h if g1 inverse g2 is in h. So this will just say that this will say that yx inverse xy is in z of c minus k plus 1 h. So this will say that x inverse y inverse xy is in z of, sorry, this is g, c minus k plus 1 g. So hence, therefore, gk plus 1, which was g, this commutator subgroup of g and gk, which was a sub of uh, commutator subgroup of g and z, c minus k g. We have proved now that this is a subgroup of z of c minus k plus 1 g. Hence, our induction process is done. Hence, by induction, gi is a subgroup of z of c minus ig for all I equals 0, 1 to c. Okay. So once this is done, the rest is very easy. Why? So in particular, for I equals c, what happens? We have gc, which is a sub of z c minus c g, which is nothing but g0 z g, g0 g, z0 g, correct? And this is by definition, z0 g is by definition identity. So that implies what? See, you are saying that gc is a sub of identity. That will imply gc to be just identity, right? So let's look at our theorem, what we wanted to prove. We wanted to prove that if it is nilpotent, then it is if it is nilpotent, then GC is identity. GC is 1, which is same as, I mean, sometimes we write 1, sometimes we write bracket T, that is the trivial root, which means same. But then this part is still not done, right? C is the smallest positive integer, right? Okay. So let's try, let me write down the argument for that. So we need to now show that C is the smallest possible integer such that GC is 1. Okay. So, okay. So let's prove it. Okay. If possible, let GD is 1 and D is strictly bigger than C. Now, one can easily prove in a similar fashion that uh, if g of d is 1, this will imply the inequality which we wrote will still hold. That is, g of d minus I is a sub of z of I of g for all I belongs to 1 to for all I belongs to 0, 1 to d. Okay, so this I'm just saying it's easily one can easily prove. This you should really try to do it at home. Okay. Okay, I there is a mistake which I have done. So I have written, if possible, let GT is one and then D is more than C, right? So if possible, I should assume actually that D is less than C, not more than C. I want to prove that that is the smallest. So I should assume that if possible, there is something smaller and then get to a contradiction. Okay. So what do we get then? So for I equal to D, what do we get from this? From I equal to D, we get G of D minus D, which is G0 is a sub of GD of G. Now what is G0? G0 is by definition G. So I'm saying ZD is a sub of G. So what does this imply? This implies ZD of G has to be G. Okay, but this contradicts. Can someone tell me what it contradicts? But this contradicts the fact that C is the nilpotency class, because we are already saying that GC is 1 and C is the uh, smallest such
Constant
possible
integer.
integer, right? But what do we have? But here we have D is less than C. So this is not possible. Hence, C is the smallest such integer such that GC is 1. Okay. So this proves the direct way, the proving that nilpotent implies GC is 1. Okay. If one wants to prove the converse, okay, uh, the converse is exactly similar. I don't want to do it. The proof will exactly follow the same way. The converse exactly follows uh, similarly. So basically, first you assume that I'll just write down the steps and leave it up to you to check. First, you assume that GC is 1. From this, you just first prove that you prove that inequality, right? You prove that G of C minus I is a sub of Z of I G. And then step 2, what do you do? Step 2, you put I equals C to get GC of G is G. Then you have to prove that nilpotency class is exactly C. That is, you have to prove that less than C, G of anything less than C won't be G. So what do you do? You say that again, you say if possible, let ZD of G is G, sorry, ZD of G is G, and from this you have already proved in the first part of the theorem that this will imply that G, uh, it will imply, what will it imply? Gi is a sub of Z of C minus of G, and this will say that GD is 1, which is a, so for I equals D, it will say that GD is 1, which is a contradiction. So I leave this I leave these to the audience to figure out, to write down the details, but almost everything is there. I think the only part which we haven't proved is this we haven't proved, but which should follow exactly. If you follow the proof of the previous course part, it should be kind of clear. Okay. So I think I stop this session here with this theorem, and we will continue next time. So if there is any question, I can take it now. If you have any doubts or anything to ask. Okay, so if there is no question, we end this session here.